Hello, everyone. I am Philip, and this is Adrian, and this is our CMP 152 compiler.
For our project goal, the compiler reads a subset of Python code, identifies errors, and if there are none, it produces executable intermediate code. The objectives are to detect syntax errors with line numbers, continue analyzing even after errors, generate target code for 3 test cases if there are no errors, and to demonstrate full compiler pipeline.
Moving on to the lexical analysis, our lexer performs character by character scanning, token classification, Python indentation handling, line column tracking, and comment plus white space skipping. So the goal of our lexer is to produce a clean, structured token stream for the parser.
Token classification. It's accomplished using fixed keyword operator and delimiter tables. Identifiers are recognized through DFA-based scanning and then checked against the keyword table to ensure reserved words like if, while, definition, and return are not mistaken for variable names. This table-driven classification enforces deterministic token types and is central to predictive parsing.
Moving into our lexical regular expressions, our lexical specification is designed around regular languages for deterministic scanning. These patterns ensure that every lexeme in our language can be recognized without backtracking or ambiguity. The simplicity of this pattern allows for the lexer to run on O(n) time over the input source while producing high-quality errors.
For lexical analysis, identifier detection uses deterministic finite automation. The lexer begins in an initial state requiring a letter or an underscore, followed by looped acceptance of alphanumeric characters. No backtracking is needed.
Moving into our indentation handling, Python's indentation rules represent block boundaries. Our Elixir fully implements this by examining lead white spaces on each line, comparing indentation to a maintained stack, and emitting indent and dindent tokens to explicitly mark block structure for the parser. This approach transforms Python's white space-driven structure into a tokenized context-free grammar.
For syntax analysis, the parser in our compiler is a fully handwritten recursive descent parser. It uses LL1 logic, meaning it'll scan left to right, produce a leftmost derivation, and use one token look ahead. Um, with one token look ahead to choose productions deterministically. This parser directly implements our grammar rules, consuming tokens, and constructing a detailed parse tree. Some of the parsing responsibilities include enforcing the grammar, managing nested blocks through indent and dedent, reporting syntax errors immediately, creating structured nodes for transformation into the AST. Recursive descent was chosen because our grammar is straightforward and easy to debug.
Moving into context-free grammar, our grammar is carefully crafted to be LL1 support, which supports precedence and aligns with Python semantics for blocks.
Follow sets guarantee that empty productions do not cause conflicts and that rule selection remains deterministic even at grammar boundaries. No first follow overlap was observed, confirming their suitability for LL1.
Moving into our parse table construction, we use first follow. We created a LL1 parser table mapping, which takes non-terminal and look ahead production. And here are some sample entries. So we have non-terminal look ahead in production, and within the non-terminal, we have statements, expressions, and a factor. And then within the look ahead, we take if, identifier, and integers. And in production, we have if and then assignments, term expression, and expressions with quotations.
One example of a parse tree that's generated by our compiler is for arithmetic expressions. For our input x equals 3 plus 5 times 2, we generate an assignment, which further expands to indent equals an expression. Expression goes down to term plus term, by which term goes to factor into 3, and term turns into a multiplication of 5 times 2. And it'll produce 3 plus 5 times 2 equals x.
Moving into our second example, which is an if statement. First, we have the source code on the left, which is the if x is greater than 0, then y is equal to x. Moving into the parse tree, we have the if statement is separated into three subtrees, where the left subtree is an expression, where we first call the expression that goes into x greater than 0. So we take the greater than, and then the subtrees of that is x in 0. And then moving to the right subtree, we have block, which is moved into an assignment and then separated into indent and expression. As you can see, y is equal to x is indented and then turns into y and an equal x.
For the overview of our AST, after parsing, we convert the parse tree into an AST. The AST eliminates syntactic constructs such as parentheses, colons, keywords, and intermediate nodes. Each node directly represents a semantic construct such as an assignment node, binary op node, literal node, variable node, if node, or while node. The AST is compact, expressive, and forms the foundation of semantic analysis and code generation.
And this is our example, our arithmetic example of AST. The following AST illustrates how the compiler represents the expression x is equal to 3 plus 5 times 2. After parsing, the AST removes unnecessary syntactic details and encodes operators precedent structurally.
The core AST node definitions, implemented using Python classes that capture the essential meaning of each construct. An assignment node stores a variable name and the expression assigned to it. A binary op node contains the left operand, the operator, and the right operand, allowing the compiler to interpret arithmetic operations correctly. Literal values are represented using our literal node, while identifiers refer to variables represented by the variable node. This is the semantic backbone of our entire compilation process.
Now, our semantic analysis overview. So the purpose of a semantic analysis enforces the meaning of the program and catches logical type errors that are syntactically correct, where parse trees alone cannot detect. Variables are defined and initialized before use. Operators are only applied to compatible types. Scopes follow Python-like rules using nested symbol tables. Functions have valid parameters and return statements. And an example of an invalid operation would be string plus boolean, which hopefully are going to be rejected.
For our simple table, we model Python-like lexical scope using a stack of scope objects. We have the global scope that's created once at startup. We have an enter scope, which pushes a new scope for if, while, for, and functions. An exit scope, which will pop back to the enclosing scope. Define, which will record new variables and functions in the current scope. And lookup, which searches from the innermost scope outwards.
Our semantic rules for assignments. So assignment nodes first evaluate the right-hand expression, then bind the result value to the variable name in the current scope. This prevents use before definition and enforces consistent types whenever a variable is reassigned.
The semantic rule for our operations. Binary operations will first analyze both the operands, infer the types, and then enforce that the operator is applied to compatible types. For example, for arithmetic operators, the plus, minus, multiplication, divide, modulo will require numeric operands, while plus will also allow string-to-string concatenation. This will prevent invalid expressions like 10 times high or true minus 3.
Moving into our variable semantic rules, variables reference must resolve to a symbol in the nearest active scope. If a name is not found or is found but never initialized, the semantic analyzer reports an error. This prevents reading garbage values and makes sure every variable use is meaningful.
Control flow semantics. If semantics, the condition expression is analyzed and must have or infer to a Boolean type. Each branch, such as if, else if, and else, is analyzed in its own scope, so variables declared inside branches don't leak unexpectedly. This will prevent nonsensical conditions like if hello x equals 1 from silently passing type checks. For while loops, the while loop is also required to be Boolean-like. The loop body is analyzed in a new lexical scope, which matches how Python treats variables defined inside loops. This lets us catch errors like using the wrong type in that condition or relying on variables that are never initialized in the loop.
Moving on to data flow analysis, our compiler data flow analysis includes things like live variable analysis, reaching definitions, constant propagation, and dead code elimination. First, we have a definite assignment. Every variable must be defined and initialized before it is used. We implement via a symbol table, and we also initialized and visit variable. Then we have type, flow, and safety. expression types are inferred and then checked for compatibility, ensuring operators are only applied to valid types. Then we have scope-aware name resolution, where names are resolved through a stack of scopes. So definitions flow correctly through nested blocks and functions. And then we have function contracts, which function calls are checked against their defined parameters and return statements are validated to appear only inside functions. Moving on to code generation overview, the code generation transforms the AST into a low-level three address code, short for TAC, intermediate representation. Each TAC instruction is represented as a quadruple. We have the op code, which is OP, argument one, argument two, and the result, which closely resembles a simple assembly instruction. In this phase, the compiler does not execute any expressions. Instead, it emits a structured instruction that can later be interpreted or executed by a virtual machine or the backend.
For example, generating a tag for expressions. Expression code generation operates using a post-order traversal of the AST. It'll first visit the left subexpression and produce a temporary or variable name. It'll then visit the right subexpression to obtain another temporary. And after both sides have been evaluated, it emits a three-address instruction that combines these values into a new temporary. One example would be the expression x equals 5 plus 3 times 2. It's lowered into the TAC by evaluating the multiplication first, producing t1 equals 3 times 2. It then computes the addition as t2 equals 5 plus t1. And finally, it stores the result into a variable with x equals t2.
So TAC for assignments. So for assignment statements, the code generator does two things. First, it generates TAC for the right-hand side expression, and then second, stores the resulting temporary directly into the target variable. So an example of this would be x is equal to 5 plus 3 times 2. And since we do multiplication first, t1 becomes 3 times 2.
Generating tag for control. Conditional and loop statements are translated into label-based control flow that closely resembles real assembly. The code generator creates fresh labels for branch targets using the new label. If it inserts conditional jumps such as if false or if true to evaluate decisions and control the flow of execution. It emits unconditional go-to instructions to skip over code blocks or to return to the top of a loop.
So this is our end-to-end compilation. And within the following slides, you're going to see all the stages of the compiler and our source code and the mode that we choose. So first, we're going to choose the multi-line mode, and then we're going to input our source code, which is x is equal to 3, y equal to 5, and z is going to be an expression. And if z is greater than 10, we're going to print z is big. Else, we're going to print that z is small. We've also included commands, so we're going to go ahead and do semicolon compile, and that's going to go ahead and bring us to this next slide. We separate into three different phases, where our first one is going to be our lexical analysis, where we take each variable or reserved character. For example, x is an identifier, equals is an assignment, and integer is 3. And then we're going to separate this into our AST, which is our parser. And then the phase 3, which is going to be our semantics, just basically tells us that all our code compiles correctly and each type has a compatible operand. And now moving into our phase 4 and phase 5, we generate our TAC code, which we can see here. And then last in phase 5, we generate our assembly code or generate our corresponding assembly code, which can be seen in the screenshot. Hello, this is our CMPE 152 Python subset compiler. As you can see, we have we program commands, and we also have a choose mode. Adrian will be covering the commands, and I will be covering the different modes.
So we implemented a small little terminal user interface, just so that it's a little easier to interact with our compiler. We do have a few commands. We have the compile command, which you'll invoke after writing your code so that it will know when to compile. We have the clear command just to clear your terminal. We created a little debug mode to help us debug while we were creating the compiler, which could also just be used for debugging, finding out what errors you have. We have the help command, which will just bring up this little text and exit to exit the interactive mode as well.
Moving on to the choose mode, we have five different modes, where the first mode is the multi-line mode, where we can run full programs as in just if statements. We have a quick mode, which runs one line of code, so this can be used as like a calculator. And we also have a load file, and that's how we completed our testing. Show history to see what compiled in the past, and we just have an exit. So showing our multi-line mode, we hit one, we hit enter. And then now we're going to be going ahead and putting in some code. Um, within this code, we wanted to outline that um, our error handling and how it notifies us that something is incorrect within our code.
So
Uh,
yes, as you can see in the code that we wrote, there is a slight error. For the if statement, there is a missing colon. We just want to show our error handling that it will tell the user that there is an error and where the error is and which line.
and as you can see on line two, it expected a colon. And that's just how it handles errors. So we're going to be going ahead and writing the same program again, but this time it's going to be correct. And we'll see that our output shows all the different stages of the compiler and includes the assembly code.
Oh, you missed the
Oh, I
colon.
missed the colon. Oh, that means, let me just run this real quick and I'll show an error again. And then fix this, and then I'm going to go ahead and compile it. And then, so what we're going to see is going to be the stages of the compiler. So we choose a mode. This is our source code. And we notify that the compilation is successful. And this is going to be our end-to-end example. So first stage source code is going to be translated into the tokens lexer that we saw earlier, then goes to the parser, goes to the semantic analyzer just to verify that all variables are declared and initialized before use, that we have type compatible operands, and user-defined functions are called correctly. Moving on, we have our phase four, which is our generated TAC. And as you can see, it works. And lastly is our approximated x86 assembly that we generate. And this is just the source code from the source code to this, you'll notice that this actually it functions exactly correct. And that's our compiler demo.